Very good morning to one and all. And myself is Sudhagara Rajan, and I'm working as assistant professor in International Institute for Aerospace Engineering and Management, Jain University, Bangalore. So I've completed my bachelor's and master's in aeronautical engineering. I've done my PhD in aerospace materials, and during my PhD, I worked in a ISRO project which deals with enhancing the titanium alloys fatigue life through various surface modification technique. So that's all about me. So today I'm going to give a talk on imperative role of materials in aerospace industry. So just give me a moment. Yeah. So yes, we all want to know, first of all, what is the driving force for the materials research, whatever we are going to talk about, and why we have to do the research, and what is going on in the research and development of the materials that we have to. So what is being an impetus for the materials research? That is a very important thing which we should know, because through that only we are going to travel the entire time when during which we are spending it in materials research. So what is the driving force for the materials research? Obviously, one of the important driving forces is cost reduction. So how we are going to reduce the cost? We are going to reduce the cost through a weight reduction. Cost reduction is the cost. What I'm mentioning cost here is not only the manufacturing cost. It also includes the operating cost. It also includes the maintaining cost. Everything. Okay. So how this cost reduction is possible by reducing the weight. While by reducing the weight, what will happen? The fuel consumption will be less. If the fuel consumption is less, then the material, that effect will reach the layman, the normal person who is going to take a ticket to travel from Chennai to Delhi. That effect will be felt by that particular man. Okay, so that is a impact of cost reduction, as well as we also want to extend the service life of the aircraft parts and structures. That is also another important driving force for the materials research. That's what I have done in my PhD. So I've worked in the fatigue life extension of a titanium material, the possible surface modification techniques to enhance the fatigue life of the titanium alloys. That's what I have worked. So that is also an important driving force for the materials research. Next, what we are going to see is evolution of selection criteria of the material over the decade. So right from the 1900, what made Wright brothers to select wood and fabric cloth for their first aircraft? That is very important. What made them to select? What they made them to select? They have selected based on the weight and strength. Okay, they cannot afford more weighing steel or aluminum during that period, because the engine which they used is very less, which has a very less horsepower. For example, I'll tell you one simple comparison. Their horsepower is between 9 to 10 HP only. The engine used by the Wright brothers, the horsepower of the engine used by the Wright brothers. Okay, but currently there is one airlifter called Airbus I think it's A400. So it has 4 turboprop engines, and one engine horsepower is about 11,000 HP. Just imagine what is the difference between the Wright brothers engine and the current prevailing engines. So that much difference has become, and that much development the aerospace industries have faced. Okay, so this is just an example. So by 1900, only weight and strength played a main role in the material selection criteria. By 1920, weight, stiffness, and stiffness also came into picture by 1920. Later, by 1940, creep resistance of jet engines came into picture, because they might have faced a lot of failures due to the higher temperature operation. So the creep resistance also came into picture. By 1940, only damage tolerance also came into picture, because due to damage tolerance is nothing but a fracture toughness. So when the material or a structure should withstand the inherent flaws, so that it should not fail, and it should have a fracture toughness. So that has come into picture. Damage tolerance has come into picture by 1940. And by later 1960, supersonic transport. So a material which is used in the supersonic transport must have a property to withstand the structural integrity during the supersonic speed. That is also become a main selection criteria for the material during that time. Later, corrosion resistance has become a main picture, because corrosion is a very important area of research, as well as it is also a very important thing which has to be improved, the corrosion resistance, that we will see later. Because what makes so important, when what is a huge loss caused by the corrosion, everything we'll see in the later slides. So later, by 1970, flight range and fuel consumption has come into picture. By 1980, excuse me, by 1980, acquisition cost. By 1985, radar absorbing properties, and then by 1990, life extension and through life cost. It also came into picture. Through life cost is something like maintenance cost. And by 2000, after 2000, in a very recent days, very important thing which came into picture is greenhouse gas emission. Okay, because we have started right now thinking about the future. We are right now talking about environment. So that has become a very important criteria for the materials also, right from the materials, not only the BS4 and BS6 norms for the engines, which is came into picture for the automobiles right now. Similarly, the materials also is also selected based on the greenhouse emission, greenhouse gas emission. We'll see it in the next slide in detail. So this is the evolution of selection criteria of materials over the decade. So later, so today's outline of the presentation is, today we are going to see about the importance of the material, and in several perspectives we are going to see, in the perspective of the environment, in the perspective of the performance, in the perspective of the design, or how the material is correlated. That we are going to see. Later we are going to see the brief history. So from when, so what happened right from the right rulers. Yeah, that we are going to see, and what happened and what made them choose alloy, what made them choose their the materials for their aircraft, and how does right from the wood, right now it is right now Glare or CFRP is being a lead material in the manufacturing, how it has evolved. That we'll see the brief history. Later we'll see the current scenario, what is happening right now, and what is a very happening material in the aerospace industries, and what make them happening, or else what made them to be an important alloy in the aerospace industry. That we will see in detail in the current scenario. Later we'll see the future trends. So what is going to be in the aerospace materials? What are the interesting materials going to come for the aerospace industries? And what are the interesting characters also? That we'll see in the future trends. And later the last topic we'll see challenges or research scope in the materials research. That is very important. So what is that? What are the available challenges in the material which is currently in use? That we'll see in the challenges or research scope. So that will be very useful for the young researchers or the faculties who are going to start their research in the materials. That I think that will help for them. So this is my short outline of the presentation. And okay, as I said before, right now we'll see the importance of the material in the environmental aspect, or as in the perspective of the environment. So you know one thing, as per the Intergovernmental Panel on Climate Change, a recent shocking report is by 2050, it's about 15% of the entire global greenhouse emission is going to be contributed by the aerospace industries alone. Just imagine, 15% is a big number. Okay, then we must feel responsible to reduce that number, because the material should be developed, a lighter material should be developed, a higher operating temperature should be developed, and in such a way we have to reduce this. And that's what so for example, by reducing the 1000 kg reduction may lead to 1.1 to 1.5 percentage of reduction in the fuel consumption. Just imagine. So weight reduction plays a major role. Similarly, by increasing the operating temperature of the current alloy which is in use right now by 50 degrees, just by 50 degrees C, we may end up in increasing the efficiency of 1.0 to 1.3 percentage in the 1.0 to 1.3 percentage in the engine efficiency. So, what is the main aspect or main tool to reduce this environmental effect is by reducing the weight as well as increasing the efficiency. Increasing the efficiency can be directly contributed by increasing the operating temperature of the material. Okay, so this is how the material and environmental aspects are correlated. Later we'll see the material and performance. Obviously, material performance, immediately the engine will come into picture. If the engine is coming into picture, the thrust will come into picture. So what is the main criteria for increasing the thrust is One is weight reduction as well as second one is also operating. What the same thing what we have seen in the environment, here also it will come into here also it matters a lot. So materials used in the turbine blades should withstand high temperature, and obviously super alloys are playing a major role in this. So nickel chromium superalloy, and they are playing a major role in this. Similarly, titanium is also used there are two parts. One is very high temperature part, and another one is cold part of in the engine. We are talking is the cold part where the operating temperature will not exceed 400 degrees C, titanium will be used. 400, 450 degrees C, like for example, the compressor blade over there and all, the titanium can be used. For the combustor, in that high temperature region, the nickel superalloy can be used. And similarly, single crystal alloys has been right now. It's right not right now. Um, it's very happening right now in the turbine plates, because single crystal we all know a crystal, a normal metallography microstructure of the material, it consists of grains and then a grain boundary, and there will be several millions and millions of grains, and grain boundaries will be there in the normal turbine plate. But if it is possible to develop a material which has only one crystal, that means there won't be any grain boundary. If there is no grain boundary, there is no possibility of getting a corrosion or a weaker part in the entire region. Okay, because grain boundary is one which is prone to have a corrosion, or which is nothing but a defect, because microstructure grain is nothing but a collection of atoms which is arranged in a particular orientation. Okay, and there will be another collection of atoms, another set of atoms will be arranged in a different orientation. This two different thing will come into, if there is kept together and there is one interface which is connecting these two grains, then that is called a grain boundary. So grain boundary is a weaker part, and it has more energy, so that it can contribute the corrosions, or it can enhance the corrosion. So if the grain boundary is eliminated by using a single crystal material, then the material will have a very good property, as well as the material will be developed in such a way that the material will have a strength in one direction, the desired direction, that we can say in a proper way means the desired direction. So that single crystal application of the single crystal will also help in increasing the operating temperature by 25 degrees steady state. Okay, so that is also that is or can be also employed to enhance the performance of the engine. And later by 1980s, only the polymeric composites engine components has come into picture, and that decreases the weight and increases the efficiency. And material and design. Material and how this material and design is correlated. For example, if you want to design and develop a wing, you have to select a material which has both tensile and compressive stresses. Good tensile and compressive stresses, because just imagine, if when an aircraft is in during the taxiing, or when an aircraft is in ground, the lower part of the wing will experience a compressive stress due to the weight of the fuel, as well as the cantilever effect. The wing will be bending towards the ground, okay, right? So that and the bottom part of the wing will have a compressive stress, and so that, and similarly the same aircraft, if it is during the flight, the bottom part will experience a lift, so that the bottom part will experience a more tensile stress, and the upper part will experience a, and vice versa will be happening. So what is the material during the selection of the material? What you have to keep in mind, the material should have both higher compressive as well as tensile stress. That's how the material is also interrelated with design. Similarly, in the fuselage also, the material should have higher tensile strength and shear strength, as well as the fracture toughness should be also really good for the fuselage material. This is how the material and designs are correlated. So let's see a brief history about the material. As I said before, by 1903, when the Wright brothers used wood and fabric cloth, because their engine capacity is very less. They cannot afford a steel or aluminum during that time because of the engine horsepower, and they saw that only they have used this wood and fabric cloth. And by 1915, Junker J1, first all metal aircraft has been introduced, and the metal used here is steel. Okay. Later, the steel has a very important drawback. One is corrosion resistance. Very important. One of the important drawback is corrosion resistance. To overcome the corrosion resistance, The first de Havilland Comet, first commercial jet airline is used in 1949, used aluminum in a significant amount. Right from that time only, it has become aluminum has become a major thing in the aerospace industries, major material in the aerospace industry. By 1957, polymeric composites were used for the first time in Boeing 787. By 1957. And this is a timeline of the aerospace material applications. For example, this for 1900, for the first time wood is used. By 1920, for the first time aluminum is used. In that way, if you see, by 1900, wood was used for the first time. By 1920, aluminum alloy. And by 1930 itself, magnesium alloy came into picture. Magnesium is one of the lightest alloy possible. And among the alloys, I'm talking about aluminum, titanium, steel. If you see in that category, magnesium is the lightest alloy. And then high-strength steel came into picture by 1940. Fiberglass composites came by 1942 itself. They have started using the fiberglass composites. And superalloys came in the 1955. And then by 1950s, 55 or 56, same time period, almost same time period, titanium came into picture. And then by 1970, carbon fiber composites came into picture. And then by 1975, 70, later 70s, metal matrix composites came into picture. By 1980, reinforced carbon came into picture. Like they have started using it. And similarly, by 1982 or 85, radar absorbing materials like stealth kind of application has been used. And then by 2000, right now the GLAR is used. GLAR is nothing but glass reinforced fiber metal laminates. And that is a very important material which as GLAR as well as CFRP is becoming a very important component for the fuselage application. Let me give some numbers in the later slides to highlight their importance. So this is current scenario, what you're going to see now. Current scenario is nothing but composite material. That is the current scenario, because just by seeing this one graph, you can clearly understand how the composites is gradually increased and they have reached the top right now. For example, by Boeing 747, it's about it's less than 10% the composites. It's about it's maybe around 4 to 5%. And but right now in Boeing 787, which is a recent vehicle which is launched by Boeing, which is also called as Dreamliner, it's about 55%, 50, maybe around 50% the composites. It's made up of composites. And similarly, you can see the aluminum, how this is dropping. Right from the Boeing 747, the percentage of aluminum is dropping, and right now the composites is happening and very important component for the aerospace industries. Very important material for the aerospace industries. So this is also another solid evidence for that. And right from the DC-9 in 1965, the composites being in practice, like they are using it, but it is gradually increasing, and it has reached right now in Boeing 787 and the Airbus A380 in the 2018, I think so. By 2018, it's about Boeing 787, Boeing the Airbus A350 is used about 50% is made up of composites. Some of the important component of the composites are CFRP outer flaps, CFRP vertical vertical tail planes, and then horizontal tail planes, which is made up of CFRP, ATL for torsion, box, and elevators. So these are all some important components which is made up of composite materials. And this one solid evidence for the increase in the composite applications in the current scenario. And for example, in the A350, it's about 52% of composites are used, which is Airbus 350. And in the Boeing 787, B787, Dreamliner aircraft, it is about 50% composites is used. Okay, so this increase in composites is mainly attributed to what makes it more important, and what makes this drastic increase in the composite application is, first thing is higher specific strength. It has higher specific strength, and second one is it has higher corrosion resistance, and third one is fatigue resistance. It has a very good fatigue resistance, and fourth is higher operating temperature. So I'll give some numbers over there to highlight the importance. For example, the CFRP. It's nothing but carbon fiber reinforced polymers with 550 MPa of yield strength. It has about 1/5 and 1/3 of like 1/5 of steel's density it has, and 1/3 of aluminum. Just imagine how lighter it is. So such a light alloy, but it has a yield strength of 550 MPa. Just imagine how what a great boon it is for the aerospace industry. So that's what CFRP is playing a major role in Airbus, A380, and um, in the fuselage um, construction. Okay. Similarly, CMC, composite matrix, ceramic matrix composites. So in the ceramic matrix composites, it is an excellent candidate for the high temperature applications, so that it can be used as it is for the combustion. Okay, we don't want to go for um, uh, any coating, special coating, or anything else. You can try using it directly for the combustor application, because it can withstand up to 1400 degrees. And combustor temperature may be in between 1250 to 1300 degrees C, it will be there. So 1400 degrees C, if it can withstand, if you if it's possible, you can also apply a thermal barrier coating, so that you can extend the safe limit, design safety till further end, and we can use it. So CMC is also another tool for enhancing the performance of the engine. So not only current scenario, we are talking about the current scenario. Not only composites are in research right now, even in aluminum also they are working on 2000 series and 7000 series. 2000 series is nothing but aluminum copper, and 7000 series is copper alloy, and 7000 series is nothing but aluminum and zinc alloy. Okay, and aluminum lithium is also under investigation right now. Currently, they are working on it. Aluminum lithium is the lightest alloy among the aluminum group of groups. Okay? Aluminum alloys group, the aluminum lithium is the very lightest, because lithium has a tendency to reduce the density of the aluminum, so that at the end product will get a very lighter role. So application of titanium, not only titanium is another important material which has consistently increased their application consistently increased their application in the aerospace industry. Yeah, that's why there's one solid proof for that. In Boeing 727, which is on 1960s, just 1% of titanium is used in the entire aircraft. The percentage of titanium in the operating empty weight, just 1% in the 1960s. But right now, in Boeing 787, it's about 18%. Can you see? It's not like a big numbers like composites 50% or 52%, 30 or 40. But even though it is a very less number in increase, but there you can see a consistent increase in the application of titanium. Okay, that consistent increase in application of titanium is mainly attributed to its higher specific strength. This higher corrosion resistance is another important parameter, and similarly, it also has higher operating temperature. Comparatively, I'm not comparing this with the nickel superalloy, but comparatively, it has higher operating temperature when it is compared with aluminum and steel and other comparable alloys. And another important thing is it's composite compatible. So titanium and composites can be manufactured or else assembled together, so that it doesn't have any tendency to develop a galvanic corrosion or anything like that. Any degradable reaction won't happen if the titanium is assembled along with the composites. Okay, so its composite compatibility also led a path to its application to the increasing the application along with the composites. So this is all the current scenario in the aerospace industry, current materials which is under research. And similarly, we are going to see some of the important and interesting candidates in the future trends of aerospace. One is self-cleaning polymers. So we all know about what a tamarind, a lotus leaf. In the lotus leaf, if you have a droplet of water on it, it won't stick together. It will behave like a mercury, and it will move here and there, and it will come out just like that. Okay, so the same, nothing but it has a hydrophobic character, right? So mostly in the biomedical, they used to talk about hydrophilic and hydrophobic in order to osteogenesis, something they would call. Similarly, it has a hydrophobic character. Okay, so if it is hydrophobic, by using the same operating principle or the same theory, material can be developed, and that material can self-clean itself. If you pour a water on it, only dirt will be removed, but the water will not stick onto it. Okay, So such kind of operating principle is adopted to develop a fabric seat and carpets of the aircraft. So that is called a self-cleaning polymers is under research and might be used in the future aerospace industries. And similarly, self-healing, that is another important one. Self-healing, this is also another polymers, ceramic metal matrix composites, where it can repair itself because it is if in a composites, if there is any crack is initiated which is not visible to the inspection, what will happen? Like the failure will happen, and that failure might be hazardous. That failure may be fatal. So that if that somewhere where the crack initiated, the crack is propagating, and during the composition, the composite buildup itself, we will be having a healing material as well as the um, triggering material together in the composites in the mixture. Okay, so once the crack reaches that healing material, the healing material will get released, and there will be a triggering for material will also be there in the composites in the mixture, so that the polymerization will again occur and the material will be self-healed. Okay, so I have to, if you want to see in detail, then we have to have another separate presentation. So I'm just making it as short as possible so that I'm keeping some of the important points in the or characteristics of the self-healing repairing materials. Please bear with me. And nanocomposites. Nanocomposites is nothing but having nanoparticles like CNT, graphene plates in a composite material. So that will enhance the fracture toughness of the composites. Ceramic matrix composites. Usually, ceramic matrix composites doesn't have a very good fracture toughness. If you have some nanomaterials in the ceramic matrix composites, it will enhance the fracture toughness drastically. It's about 235% in all its reporting in enhancing the. I'll explain that in the later slides. Okay, so let's see the scope for research in the aerospace material. So one important thing we have seen the driving force and what is the important driving force for the materials research. Right now we'll go much deeper and more focusedly. We will see what are all the areas, what are all the challenges in the aerospace industries, aerospace materials that can be developed, that can be taken under serious consideration for the research. One is, first is insufficient mechanical performance. That is a very important thing, which has to be dealt very seriously. And then second is fretting wear. That is the upcoming very important problem in the engine components. Fretting wear is nothing but a where the relative motion doesn't exceed 100 microns. A very small vibration kind of relative motion between the components. That will create a fretting debris, the wear resultant, and that debris will not even get escape from that relative motion, okay, that contact. So it will just remain in between this small relative motion, and that will create a crack, and that crack will become a that crack will lead to a fatigue failure also, which is also called as fretting fatigue. Okay, that is very insidious and very hazardous, and lot of engine got failed during the flight itself due to this kind of problem. So that has to be addressed properly. Okay, and third one is stress corrosion cracking, another important failure. So stress corrosion acting together, and that can promote each other. Like for example, if the stress is high and corrosion is also happening, that stress will enhance the corrosion, and the uh, cracking like pace will be increased. So stress corrosion cracking is very important. That has to be addressed. And fourth one is very important. Corrosion, as I said before, corrosion matters a lot, because one example I've given downside, you can see corrosion problem in the aerospace materials have caused a loss of $276 billion per year. $276 billion per year in the US. That is the report. So corrosion is a very important thing to address. And then fatigue failure. Obviously, as I said before, fatigue is what is it? Insidious. We cannot expect a material is going to fail, or because fatigue failure is nothing but a failure which may cause during the safe operations of or under the yield strength itself, a material will get failed. Okay, that is fatigue during the cyclic motion. And so that fatigue failure is the important thing which has to be addressed, which has to be eliminated. So fatigue failure is another important challenge in the aerospace material. And then huge cost involved in the developing or extracting the potential material. No doubt, an important material where the huge cost is involved in extracting is titanium. Okay, titanium has a very good properties, and the application of titanium is mainly constrained due to its extraction cost. That is 5 times, several times higher than the steel. Okay, so that is a very important thing. So the people who if they are working in reducing the extraction cost of the titanium, then that's a great area of research in the titanium. Still prevailing. Still the people are working on it. Okay. So we'll see material by material. In each and material, what is a problem there it is having, and what could be the possible solution for the problem. Let's see. And first thing is aluminum alloy. It is the lightest possible alloy. There is no doubt in it. And then one of the latest possible. It's about 14% weight reduction can be achieved by replacing conventional alloy with the aluminum lithium alloy. Okay. Even in that aluminum alloy is, as I said before, so aluminum lithium alloy is the lightest one. Well, almost 40% reduction in the weight can be achieved by replacing the conventional alloy with aluminum lithium. However, this alloy has a less corrosion resistant and anisotropy. So the people can start working on this issue, then that will be a good chance for ending up in a good research or very interesting outcome. Okay. So that is a problem in the aluminum lithium alloy, which is less corrosion resistance and anisotropy issues. And then magnesium alloys. Magnesium alloy is the lightest structural material. It's about 33% and 77% of reduction in weight can be achieved by replacing a magnesium with aluminum and steel respectively. Just imagine. So 33% is lighter than 33% by aluminum, and 77% it is lighter than steel. Okay, but the mechanical strength of the magnesium alloy is very less. So and similarly, the corrosion resistance is also very less. So the people should work in enhancing the mechanical strength, corrosion resistance, and stress corrosion resistance. The people should work. Similarly, titanium alloys. Let me say one important parameter which highlights the titanium alloy applications. In A380 aircraft, just by replacing a steel with titanium will lead to a weight reduction of 5,750 kgs can be saved by replacing a steel with titanium. Okay, that in turn reduces save us 28 liters of fuel per hour. Sorry, 288 liters of fuel per hour. Just imagine how much it can contribute towards fuel consumption by the application of titanium is contributing to fuel consumption. But basically, the titanium is divided into three important categories. One is alpha alloy, and then beta alloy, alpha plus beta alloy. The alpha, it's based on the alloying element which you are adding to the titanium. In alpha alloy, it has an inferior high temperature capability, and beta alloy higher strength but inferior tensile strength it has. So that has to be enhanced. And alpha plus beta alloy, almost 70% of US titanium is this alpha plus. And Ti6 aluminum 4 vanadium, that very famous titanium alloy comes under this category. And about 50% of titanium production belongs to that category, that Ti6. So that much important it is. So it has lower hardness. So some research like heat treatment or any surface engineering has to be proposed for increasing its hardness. That is a research scope in this particular one. And then composite material, as I said before, that is a happening material in the aerospace industries right now. So in the composite ceramic matrix composites, a lower fracture toughness is an important challenge which has to be rectified. So addition of carbon nanotubes, what we are talking about in the I think current trends, we are talking about the nano composites, right? So here it comes. So addition of carbon nanotubes or graphite nanoplates could be a possible solution to enhance the fracture toughness of ceramic matrix composites. Similarly, polymer matrix composites. In polymer matrix composites, under this category only CFRP comes, which is carbon fiber reinforced polymers, right? That particular important composite material comes under this category, which contributes about 50% in the Boeing 747 as well as 777 aircraft. Okay. I think it's Boeing 787. Okay, sorry for the mistake. And then higher specific strength and specific modulus. That's higher specific strength and specific modulus. However, this carbon fiber will induce a stress corrosion, stress concentration effect. Stress concentration effect will be there because of this carbon fiber. So that The research is going on to replace this carbon fiber with CNT, graphene. The recent investigation is going on, so we have to think in that direction for the betterment of this CFRP. So these are all the research problem or research scope available in the current material which is in use in the aerospace industries. And I hope, yeah, in steel we have say further more alloys to see. Steel is nothing, it's a conventional material used in the aircraft from the earlier days. As I said, all metal aircraft in 19, I think it's in 1917, right? If I'm not wrong, it's J1 aircraft which we saw in the previous slide. So right from that time, the steel is in use. Almost gears, carriage, fasteners are the components conventionally made by steel. But the very important drawback in the steel is its lower specific strength as well as its corrosion resistance. So in order to overcome this specific strength, lower specific strength and corrosion resistance, there are several researches going on. And possible solutions are low alloy steel, which is currently under research, and nano steels is being developed to address these issues. And similarly, nickel-based superalloy. As I thought about, we are talking about the increasing the operating temperature of the material, and this is one of the important material which can be used for enhancing the performance of the engines. So, but this alloy also has a problem, which is high temperature oxidation. So, because it is exposed to the high temperature, then obviously the material is prone to the high temperature oxidation. This high temperature oxidation problem should be faced, like should be addressed. And currently, people are adding the chromium or aluminum to this particular superalloy in order to increase the resistance of um, the resistance towards the high temperature oxidation. Chromium is also found to be a potential element to enhance the stress rupture life of the nickel-based superalloy. Stress rupture. So, by alloying, this problem could be faced effectively. Okay. So these are all my references used in my presentations, and this is my contact details. If you have any queries, kindly post me. Let me try to sort it out. And thanks a lot for your time. And I hope I've given some insights about the materials research and some insights about the history and current trends and future trends and even research scope in the material science. Thanks a lot for your time. Thanks a lot for the organizing committee for this opportunity. Thank you.